table shows the ampacity of number 14 copper wire for different time durations before damage to the insulation or conductor occurs. At 1 second, the ampacity is 121 amps. At 2 seconds, the ampacity is 95 amps. At 5 seconds, the ampacity is 69 amps. At 10 seconds, the ampacity is 51 amps. At 30 seconds, the ampacity is 32 amps. At 60 seconds, the ampacity is 24 amps. At 120 seconds, the ampacity is 17 amps. At 180 seconds, the ampacity is 15 amps. At 300 seconds, the ampacity is 12 amps. At 600 seconds, the ampacity is 10 amps. As you can see, the ampacity of number 14 copper wire decreases as the time duration increases. This is because the wire heats up over time and the heat can damage the insulation or the conductor. It is important to note that this table is only a guide. The actual ampacity of a wire can vary depending on factors such as the ambient temperature and the type of insulation. It is always best to consult with a qualified electrician to determine the ampacity of a wire for a specific application. The ability of a conductor to withstand a short-circuit current for a specific duration is crucial for electrical safety and system protection. Several factors influence this withstand capability, including the conductor material, size, insulation type, ambient temperature, and the presence of any protective devices such as fuses or circuit breakers. Copper is a commonly used conductor material in electrical wiring due to its high conductivity and relatively good resistance to corrosion. The size of the conductor, typically expressed in American wire gauge, or AUG, dictates its current carrying capacity and its ability to dissipate heat. Larger conductors have lower resistance and can handle higher currents for longer periods without overheating. The insulation surrounding the conductor plays a critical role in preventing short circuits and protecting the conductor from environmental factors. Different insulation materials have different temperature ratings, which determine the maximum temperature the conductor can reach before the insulation begins to degrade or fail. Common insulation types include thermoplastic high heat resistant nylon coated, cross-linked polyethylene, and rubber. The ambient temperature surrounding the conductor affects its ability to dissipate heat. High ambient temperatures reduce the conductor's ampacity as the temperature difference between the conductor and the surroundings is smaller, leading to less efficient heat transfer. Electrical codes, such as the National Electrical Code, or NEC, specify ampacity correction factors for different ambient temperatures. Protective devices, such as fuses and circuit breakers, are designed to interrupt the flow of current in the event of a short circuit or overcurrent condition. These devices have specific time current characteristics that determine how quickly they will trip under different fault currents. The coordination between the conductor's withstand capability and the protective device's tripping characteristics is essential for ensuring that the conductor is protected from damage during a fault. To determine the amount of ampacity a number 14 copper wire can handle for a certain amount of time before damage occurs, one must consider the conductor's temperature rating, the ambient temperature, and the characteristics of any protective devices in the circuit. The temperature rating of the conductor insulation is a critical parameter. For example, a conductor with a thermoplastic high heat resistant nylon coated insulation rated for 90 degrees Celsius can withstand higher temperatures than a conductor with a thermoplastic insulation rated for 60 degrees Celsius. The NEC provides ampacity tables that list the allowable ampacities for different conductor sizes and insulation types under specific conditions. These tables are based on the assumption that the ambient temperature is 30 degrees Celsius. If the ambient temperature is higher, the ampacity must be derated using correction factors provided in the NEC. When a short circuit occurs, the current flowing through the conductor can be many times higher than its normal ampacity. The conductor's temperature will rise rapidly due to the increased current. The amount of time the conductor can withstand this high current depends on its thermal capacity, which is the amount of heat energy required to raise its temperature by 1 degree Celsius. The thermal capacity of a conductor is proportional to its mass and specific heat capacity. Larger conductors have higher thermal capacities and can withstand higher currents for longer periods. The formula for calculating the temperature rise of a conductor during a short circuit is as follows: delta temperature equals I squared times R times T divided by mass times specific heat capacity, where delta temperature is the temperature rise in degrees Celsius, I is the short circuit current in amps, R is the conductor resistance in ohms per unit length, T is the duration of the short circuit in seconds, mass is the mass of the conductor in kilograms per unit length, and specific heat capacity is the specific heat capacity of the conductor material in joules per kilogram per degree Celsius. Using this formula, it is possible to estimate the temperature rise of a number 14 copper wire under different short-circuit currents and durations. However, it is important to note that this is just an estimate, as the actual temperature rise can be affected by several factors, such as the presence of other conductors in the same conduit, the ventilation of the enclosure, and the thermal conductivity of the surrounding materials. In practice, wire manufacturers often provide time current curves that show the withstand capability of their conductors under short-circuit conditions. These curves are typically based on experimental data and take into account the various factors that affect the conductor's temperature rise. These curves can be used to select the appropriate conductor size and protective device for a specific application. For example, if a number 14 copper wire is expected to experience a short-circuit current of 75 amps, the time current curve can be used to determine how long the conductor can withstand this current before its insulation is damaged. If the time current curve shows that the conductor can withstand 75 amps for only a few seconds, a fast-acting fuse or circuit breaker should be used to protect the conductor. It is important to consult the manufacturer's specifications and the NEC when selecting conductors and protective devices for electrical installations. The NEC provides specific requirements for conductor ampacity, overcurrent protection, and short-circuit protection. These requirements are designed to ensure the safety of electrical systems and prevent fires and other hazards. In addition to the factors mentioned above, the type of termination used to connect the conductor to equipment can also affect its withstand capability. Poorly made or loose connections can create hotspots that increase the conductor's temperature and reduce its ability to withstand short-circuit currents. It is important to use properly rated connectors and to ensure that they are installed correctly. Regular inspection and maintenance of electrical systems can help to identify and correct any potential problems before they lead to failures or hazards. This includes checking for loose connections, damaged insulation, and signs of overheating. In summary, the amount of ampacity a number 14 copper wire can handle for a certain amount of time before damage occurs depends on several factors, including the conductor's temperature rating, the ambient temperature, the characteristics of any protective devices in the circuit, and the quality of the terminations. It is important to consult the manufacturer's specifications, the NEC, and a qualified electrician to ensure that electrical systems are designed and installed safely and correctly. The information provided in the initial table serves as a general guideline, but it is essential to consider the specific conditions of the installation when determining the appropriate conductor size and overcurrent protection. Remember that exceeding the conductor's ampacity or allowing it to be subjected to excessive short-circuit currents can lead to insulation damage, conductor melting, and potentially fire hazards. Therefore, it is crucial to prioritize electrical safety and adhere to established codes and standards. In practical applications, engineers and electricians use specialized software and tools to perform short-circuit studies and coordination studies. These studies help to determine the available fault current at different points in the electrical system and to select the appropriate protective devices to ensure that the conductors are adequately protected. Short-circuit studies involve calculating the magnitude of the fault current that would flow in the event of a short circuit at various locations in the system. This calculation takes into account the impedance of the power source, the conductors, and any other equipment in the circuit. Coordination studies involve selecting the appropriate time current characteristics for the protective devices to ensure that they will trip quickly enough to protect the conductors from damage, while also minimizing nuisance tripping. These studies often involve plotting the time current curves of the conductors and the protective devices on the same graph to visually verify that the protective devices will trip before the conductors reach their thermal limits. The NEC provides guidance on how to perform short-circuit studies and coordination studies. It also provides specific requirements for the selection and installation of overcurrent protective devices. These requirements are based on the results of extensive research and testing and are designed to ensure the safety of electrical systems. In addition to the NEC, other standards, such as those published by the Institute of Electrical and Electronics Engineers, or IEE, provide more detailed guidance on electrical system design and protection. These standards cover a wide range of topics, including short-circuit calculations, coordination studies, and grounding and bonding. It is important for engineers and electricians to stay up to date on the latest codes and standards to ensure that they are designing and installing electrical systems that are safe and reliable. Continuing education and professional development are essential for maintaining competence in the electrical field. In conclusion, understanding the ampacity limits of conductors and the factors that affect their withstand capability is crucial for electrical safety and system protection. By following established codes and standards, performing thorough short-circuit studies and coordination studies, and using properly rated equipment, it is possible to design and install electrical systems that are safe, reliable, and efficient. The provided ampacity versus time data offers a starting point, but always consult with qualified professionals and relevant documentation for specific applications and to ensure compliance with all applicable regulations. Electrical work should only be performed by qualified and licensed individuals. Improperly installed or maintained electrical systems can pose serious risks to life and property. Always prioritize safety and seek professional assistance when dealing with electrical systems. Furthermore, consider the impact of harmonic currents on conductor ampacity. Harmonic currents are non-sinusoidal currents that can be generated by various types of electronic equipment, such as variable frequency drives and uninterruptible power supplies. These currents can cause additional heating in conductors, which reduces their ampacity. The NEC provides guidance on how to direct conductors that are subjected to harmonic currents. When designing electrical systems that will serve loads that generate harmonic currents, it is important to carefully consider the impact of these currents on conductor ampacity and to select conductors that are adequately sized to handle the additional heating. The use of harmonic filters can also help to reduce the level of harmonic currents in the system and improve conductor ampacity. Another important consideration is the altitude at which the electrical system is installed. At higher altitudes, the air is less dense, which reduces the conductor's ability to dissipate heat. The NEC provides correction factors for conductor ampacity at different altitudes. When designing electrical systems that will be installed at high altitudes, it is important to direct the conductors accordingly to ensure that they are adequately sized to handle the load. The type of raceway or cable tray used to support the conductors can also affect their ampacity. Enclosed raceways, such as conduits, can restrict the flow of air around the conductors, which reduces their ability to dissipate heat. Open raceways, such as cable trays, provide better ventilation and allow the conductors to operate at higher ampacities. The NEC provides tables that list the allowable ampacities for conductors installed in different types of raceways. When selecting a raceway for an electrical system, it is important to consider the ampacity requirements of the conductors and to choose a raceway that provides adequate ventilation. The presence of other heat-generating equipment near the conductors can also affect their ampacity. Equipment such as transformers, motors, and lighting fixtures can radiate heat that increases the temperature of the conductors. The NEC requires that conductors be installed in a manner that minimizes the effects of heat from other equipment. This can be achieved by providing adequate spacing between the conductors and the heat-generating equipment or by using heat shields to block the radiant heat. In addition to the factors mentioned above, the quality of the power supply can also affect conductor ampacity. A poor quality power supply can introduce voltage fluctuations and harmonics that increase the current flowing through the conductors. This can lead to overheating and reduce conductor life. It is important to use a high-quality power supply that provides a stable and clean voltage to the electrical system. Regular monitoring of the power quality can help to identify and correct any potential problems before they lead to failures. Finally, it is important to consider the long-term effects of aging on conductor ampacity. Over time, the insulation on conductors can degrade due to exposure to heat, moisture, and chemicals. This can reduce the conductor's ability to withstand high temperatures and short-circuit currents. Regular inspection and testing of conductors can help to identify any signs of degradation and to replace the conductors before they fail. A comprehensive electrical maintenance program should include periodic insulation resistance testing, thermal imaging, and visual inspections. These tests can help to identify potential problems early and to prevent costly downtime.